You can actually use the data mine algorithm to perform a two-way segmentation. Select two-way segmentation here, and then the algorithm details are shown down here. This two-way segmentation algorithm defines segments with respect to maximizing differences across two response variable ratios now, instead of just one response ratio, as we did in the earlier examples. Each ratio needs to be a workspace. The example we'll use here is to segment across the dimensions of lifetime gambling problems and past year gambling problems. To do it, just select two-way marginal ratios from this drop down here. Select the predictors that you want to include in the algorithm, just like last time. To make it interesting, I'll choose them all. In each case, I'm choosing the cleaned up version that we went through in the very beginning of this tutorial series, showing how to group up levels within each predictor. Name the data mine run. I'll call this data mine run two-way 1. Pick the workspaces of interest, so gambling problems lifetime and gambling problems last year. Where the weights or offsets are different between the workspaces you chose, the minimum observations per node here needs to be selected carefully. Here, the sum of obs is the same for both workspaces, 2,867. So it's fine to choose the same minimum segment size here. But if different weights applied, you might have one workspace with 200 here, for instance, and 2,000 here, because you chose different weight variables for each of the two workspaces. The minimum segment size in that case up here would need to take that into account. The minimum segment size would need to be far less for the workspace with a lower sum of obs than the workspace with a higher sum of obs. We'll choose a minimum segment size of 20 in each case to really get a lot of segments, each one with very few cases in them, just to illustrate the complexity of how it works. So once we've selected our parameters here and we're happy with the name and the predictors that we're including, click Fit Machine Learning Algorithm. Now this two-way will typically take a little bit longer than the one-way. Okay, for a two-way segmentation, the definitions page contains a table. Similar to the one-way, it contains the predictors that make up the segment definition, as well as the criteria that have to be met within each predictor in order for a record or case to fall into that particular segment. But it's got the response obs ratio for each of training and validation sets, like in the one-dimensional data mine, but it's also got the equivalent columns for the second workspace. So this is saying, for instance, let's just sort this by, so this is saying for the first workspace, which was lifetime gambling problems, the ratio in the training data was 2.46, or the average gambling addiction score was 2.46. The average gambling score in the validation data was 2.18. However, for the past year gambling score, which will be lower than the lifetime gambling score in all cases, the ratio is 2.03 for this segment for the training data and 1.61 for the validation data. Recall that the reason why the past year gambling score will always be lower than the lifetime gambling score is because the gambling score itself was a count of whether someone answered yes to have you ever been bankrupted or have you ever stole in order to pay for gambling. And it was either have you ever done this in your lifetime or have you done this in the past year. So obviously if they've done it in the past year, then they have also done it in their lifetime. They will never answer, yes, I've done it in the past year, but no, I haven't done it in my lifetime. In addition to the definitions table, for the two-way segmentation, we also get a couple of more charts. The reason why we get these charts now is because we have two dimensions to work with. We've got gambling problems lifetime on the bottom axis here, and gambling problems last year. And there's this chart here, and there's a similar chart down here. What these basically are is each bubble represents one of the segments. So this is segment 10, that's the segment label as per the first column here. The bubble size represents the relative size of that particular segment, so it's the number of observations that are in it, as measured by training data in workspace 1, which was the workspace on the bottom axis here. Now, it's the position of the bubble is the lifetime gambling score along this axis. So it's 2.46. So it's if we could see the number here on this axis, it'd be 2.46. Whereas on this axis here, the number would be 2.03. So we can say that the lifetime gambling score for people in this segment was 2.46, and the gambling score last year, or in the past year, was 2.03. The bubbles are color coded. We can imagine that this segmentation plot has been divided into 4 quadrants. Imagine there's a line running down here which separates the average lifetime gambling score, which was 0.23, I think. And imagine there's another line running across here, which is the average past year gambling score. So there's a line running down here, a line running across here, each of which cuts the axis at the average value. And because we've got this line running down here and this line running across here, there's effectively 4 quadrants. So there's these bubbles here where the segments represented by these bubbles are in the top right quadrant. The bubbles represented in this quadrant up here are in the top left quadrant, bottom left quadrant, and bottom right quadrant, and so on, and they're color coded accordingly. So any bubbles where the lifetime gambling problems was above the overall average and where the past year gambling problem score was above that overall average, the bubbles are colored red. Any segments where the lifetime gambling score is above average, but the past year gambling score is below average, so in other words, we're in the bottom right quadrant here, they've been colored yellow, and so on for the green and the blue. So that helps you pick out what segments exhibit different characteristics across each of the response variables of interest. So what characteristics define people where they tended to have relatively lower lifetime scores, say, but much higher past year scores? So they would be colored green. There aren't many of those. Or say what people have had really bad lifetime scores but haven't been so bad in the past year. They would be the yellow. Below that is a similar chart, but for each segment we see the value of each ratio for the training and validation data. Recall that these bubbles here just plot the training ratios. The validation ratios aren't actually shown in any way on this particular chart, but here they are. The head represents the training data for this segment, or the training ratio, and the tail represents the validation ratio. So a good segmentation is one where the head and the tail are close together, because it means that for this particular segment, the training ratio and the validation ratio are quite close. A good segmentation is one with short tails, a bad segmentation is one with long tails. Two-way segmentations like this are useful where you need to make a trade-off between 2 outcome variables. Maybe you're trying to find segments of the population that simultaneously have both high gambling scores and high substance abuse scores. There were questions in the gambling survey data about alcohol and substance abuse. So one workspace used in the two-way segmentation might be gambling problems, and the other might be some composite of alcohol and substance abuse. This is the final video in the Preddle series on modeling social science data. Thank you for listening to this Preddle tutorial. We hope you find Preddle useful and fun to use. Please feel free to email us at admin@preddle.com with any questions or feedback.